and have obliged us with his valuable time. Let us begin with formal introduction. And Dr. M.V. Reddy began his journey of research in the area of material science and engineering when he obtained his PhD back in the year 2003 from University of Bordeaux, France. Then he worked from 2003 to 2019 in the Department of Material Science and Engineering at National University of Singapore. And then he moved and relocated to Canada, wherein from 2019 till 2021 August, he worked at the Center of Excellence in Transportation, Electrification and Energy Storage, Hydro-Quebec, Canada. And currently, recently, he switched on as a senior professional researcher at New Graphite World, Montreal, Canada. So, sir has a very vast experience of over 20 years internationally working in the field of material science, energy storage, solar cells, and other. And he has published more than 200 research papers, and his H index is above 66 with over 16,000 citations. Dr. Reddy is also considered within the top 2% highly cited researchers in energy and is ranking 1002 out of 186,500 researchers in 2020. So we are extremely grateful to you, sir, that you spared your valuable time. And Dr. Reddy has also given many plenary and keynote sessions and invited talks nationally and internationally as well. And he is considered as an outstanding researcher and has received many awards. Some worth mentioning are Outstanding Science Mentorship Award, which he received for his work from 2010 to 18 from Ministry of Education, Singapore, and even an Inspiring Research Mentor Award from NUSHS. He is also a life member of International Care for Diffraction Data USA. He is an elected committee member in Institute of Physics, Singapore. And he has served as honorary auditor for IPSS and MRS Singapore. He is also part of various national and international review committee of various journals. So with this, I formally welcome you, Dr. Reddy, to this session of our faculty development program. And I invite you to kindly take on the dais and deliver the invited talk, please. Dr. Reddy, please.
Okay, thank you, Professor Singh, for your kind words, and then especially thanks for all the workshop organized, including that Delhi Technological University and also AICTE for the sponsoring this event. I hope my slide is visible, and also, so whatever the voice, maybe now it is better slightly.
It's visible.
So whatever this slide is able to move, yes?
Yes, it's working. It's working fine.
Okay. So again, I will start. So again, without any further delay, thanks for the organizers for the kind invitation and introduction. So and also, so today I'm going to discuss, since the workshop is related to the green energy, materials, manufacturing, etc. So again, I will focus on mainly something like I saw that different type of program, different type of wonderful speakers. So maybe I'll focus mainly on the energy storage, what are the material manufacturing, some fundamentals, etc. So also today I would like to thanks, also like this talk is dedicated to my late father. So it's the third death anniversary. I think today is almost like almost like 8/10/2018. So again, so as you can see clearly, this workshops has been covered by the various eminent speakers. I think today is the last day. I think you people are familiar with different type of the topics. So I think what are the slides I'm talking, maybe not more like slightly different, so that I'm going to convince you that although I'm not really mechanical engineer, still I work with that mechanical engineering department. There is a called the materials engineering. So that's why some particular slides are really so especially importance of additive manufacturing or something like composite preparation, that also very useful for our energy storage, especially for ceramic membranes. So some techniques may be useful. So So before I'm going to introduce, presently I based in Canada, where the Quebec state, so both French and English speaking colony. So again, so in addition to like other type of, again, we can see something extreme cold climate. Also now, especially during this October, so we can see something all green tree color is changing to the yellow, or sometimes different type of colors we can see depending on the some trees, etc., or depending on the climate, etc. So this is the outline of my presentation. So again, since I try to focus something like material manufacturing, processing and characterization techniques, and especially to before I'm like to include some fundamentals, I think that will be very useful for the, for example, people are doing with EV or some other type of the like materials manufacturing, etc. So again, the importance of what example research. So that's why some of the few examples. So we've been trained in the area of what I call the material manufacture, material synthesis, or whatever it may be, especially related to the energy storage, etc. Some students are able to present in the something like, for example, few papers in the international journals, as well as some students are able to present in the, for example, science and engineering fair held in Singapore, as well as few other parts of, for example, in Intel International Science held in America, Europe, or in Japan, etc. So these are the small groups within, especially Singapore, as well as almost like say, 6 to 7 giant PhD students have been trained in our laboratory at National University of Singapore. Also, in addition, we've been worked with various international exchange students. So these are my small collaboration within Singapore, especially mainly many students have come to here just to train in my guidance in the especially battery materials, etc. So so these are my research interest. I think I will tell the importance of the material manufacturing or whatever that we serve, especially for the different area when it's positive electrode, negative electrode, and electrolyte, etc. Uh, Again, I'm going to just give introduction on this materials, human history. I think it has started from Stone Age, Copper Age, Iron Age, and Rubber Age. Especially Silicon Age had made them to think in a different way. Especially, for example, discovery of vacuum tubes or computer, for example, or iPhones, etc. All the casing has come. I think this area, for example, composite cages means at the time a lot of mechanical means like people have looked into the lightweight materials, alloys, etc., super alloys, and especially year 2000, that means there is a lot of interesting things has been occurred, and especially people are talking about the functional materials or nanotechnology, etc. And year 2000 onwards, molecular age. Now future, always people are talking about the intelligent and low cost carbon age material. For example, again, always talk about green energy materials manufacturing, whatever the way you do, always they're talking about some intelligent, and always you to reduce the, always talking about the carbon economy, etc. And related to the mainly related to the energy, environment, and healthcare. So again, I mentioned that the importance of this particular three hot areas. Again, our job is to maintaining sustainable environment and healthy lifestyle, especially waste management, especially reducing the air pollution, etc. These are all things are needed for the improvement of any smart city development. That's why, so we need something like green energy in terms of renewable energy. What are the materials are there? I think this is very important. Again, materials are we broadly classified based on utilities. Again, so I think some materials, for example, each technology, especially building materials, also people are talking about phase change material or green concrete, etc. It depends on, but also electronic materials and energetic materials, and especially engineering material, for example, super alloys and steels, etc. Based on the physical properties in terms of the magnetic, optical, for example, people are talking about the electrochromics or different type of the, like photonic material, etc. And example dielectric. Today we are going to focus on the energy storage materials, and also a few others, especially CO2 capture, etc. So mainly I focus on some promising materials for the manufacturing and the what are the materials for electric vehicles or the grid applications. So again, to solve the present environmental problems, I think we need always green, renewable, and clean technology. Again, this is varies depending what type of this. For example, here we have a lot of water. That's why, so here the hydroelectricity is very famous. So that specific places like we in like India and Middle East, there is a lot of heavy sun, solar energy. So there, I think the solar energy is a little bit alternative. Again, in general, the battery materials are the one they can use it for the EV. So that is very useful, especially if we talk about the major city, including Delhi or we can reduce the pollution. Again, remember, so although if you want to reduce the like use of this particular battery materials or batteries, I think main issue is the cost. Always they see that anyway. I'm talking about the still, if you keep people are using more batteries or some improvement in the technology, I think still we can reduce the further reduction in the cost of the batteries. So I'll tell you what are the real challenges, especially so why the cost of the materials is slightly higher, and also what are the possible reasons, either due to raw materials or some problem with the energy density, etc. I'm going to discuss more details in this particular workshop. Anyway, we have other type of things, especially fuel cells, hydrogen storage, materials, photocatalytic and water splitting, especially wind and mechanical, and different ways of we can get it. Again, energy storage or renewable energy technology or environmental engineering is an interdisciplinary area. Sometimes we need something expertise in some chemistry or engineering. If you talk about EEE, materials, production and mechanical and automobile engineering, again, so these are all the people have to work together. So especially, so in terms of the material development or material manufacturing is very important. Always sometimes you want to make high energy density, you have to look for something like novel materials. Only this type of discovery, only we can do the universities. So that's why universities or IITs or NITs, that's why a lot of young students or you have a lot of intelligent brain. I think you people can concentrate in different directions. At least we can contribute to solve the future energy crisis, etc. So this is one example is for example battery. Suppose you want to use this particular battery, you want like to store the for example bulk generation, for example on the solar energy or wind energy, or future you would like to run this type of battery where for especially you run with electric vehicles. So idea behind this one, all things we are main thing is to reduce the CO2 emissions, and also other thing is that we depend on gasoline. The price, this the whole data keep on this price is going up. And remember, so for example, if you talk about the smart grid or electric vehicle, we need something higher energy. It means that we need more materials. So that's why, especially for low portable applications there, so we need energy requirement or it will be lower. That's why. So it's very important if you want to be bulk generation, the cost is a major thing. So that's why. So for this one, so best way is that you have to look for the high energy density and high capacity materials are needed for the to solve the present challenges. And these are the important one is that we can reduce the pollution use of the battery based electric vehicles. Another area is the solar energy. So that's why we would like to store this solar energy. Again, we need something low cost battery pack again. So this battery pack should be, we can reduce the unless you don't, if we can improve the energy density, we can reduce the further cost of this particular type of battery materials. So another important overall summary is that suppose people are nowadays talking about the once you were able to solve this electric vehicles, again electric vehicles integrated into the call driverless autonomous vehicles. Again, so the main issue is that here it is more things is another cost is going to occurring. For example, lidar based sensors, and for example, so again the cost is slightly higher when compared to your electric vehicles. So again, the advantage of using this driverless vehicles or whatever, there's more sensor, all the everything will monitor. So an idea is that main issue is that traffic conditions, and then especially the climate conditions, and then presently the sensors are very expensive, and we need a good infrastructure to use this type of the vehicles. Again, what I'm telling that there is a lot of opportunities to both electrical engineers, mechanical engineers, and then computer engineers to work together to solve the global challenges of this community. So these are the different type of the companies are investing, especially your people are with Teslas and then Toyota. These are the some few examples, and then spending doing this research. So now I'm going to introduce what are the importance of the, for example, electrochemical power sources. I'm going to introduce. So we know that batteries are the device which convert chemical energy into electrical energy. We broadly classified into the primary and secondary batteries. Among them, primary are like non-rechargeable, and secondary, I think we have different type of the sources are there. I'm mentioning that today we are going to focus on mainly on lithium batteries. So again, what are the fundamentals? and how, although the cost is slightly higher initially, again, if you talk about the long run, so we can reduce, especially we can reduce further cost of this particular materials. I think all people are using this type of mobile phones. Sometimes you need something like this type of the pouch cell, or if you're using with the laptops, you may use something like cylindrical cell. They call it 18650 means 18 mm, 650 like this 650 or 65 mm length cells. So again, so depending on the, you know, that laptops, you don't need too much. So we need maybe 6 to 12 depending on the batteries. So like what type of the depending on the computer. So suppose future if you run with the electric vehicles, this type of cylindrical cells nearly almost like 7,000 cells are put it in the this type of pack. Again, so this type of the, again, if you consider this type of big pack, so there is a lot of things have to take into consideration. For example, like thermal management and how the for example, the sensing everything you have to, it means more complex. That's why it is the importance of the all engineering triple E. We have to take into consideration of the, for example, battery management or charger management, etc. We have to take into consideration. Again, so nowadays, because the technology is possible, people depending on the requirement, I think a lot of fancy equipments they can get different type of fabrication. Usually, as academic researchers, sometimes irrespective or is a mechanical engineer or materials, I think usually at a university level or anything they do is a small scale. So in this cell itself, we can see which materials high energy density or high voltage, etc. You can calculate based on that one. Suppose sometimes we are able to make some promising materials, it will be really good. I think later industry or any other people are maybe willing to use your technology. They can prepare the large scale material. So this is one typical example. For example, Tesla model car. Then again, so this type of 18650 cells are put it in the almost like 7,100 cells they put it. So remember, the reason is that suppose you would like to shall be reduced to 7,100 to around for example 6,500. Only it is possible is, for example, this particular type of chemistry or this type of materials to be manufactured, that should be high energy density and high capacity. So that's why I'm going to discuss about the next coming slide, how to reduce, for example, reduce the weight of the number of cells or anything. Again, once you reduce the number of cells, automatically we can reduce the, for example, battery weight, etc. Again, so we don't have any choice now, irrespective of this one. Still, the industry taking the existing material, keep on, especially already some battery packs are in the market. So what are the important points you have to remember? So always to look for high energy density. Smart batteries means high energy density and high power density is very important. Adapt the climate conditions means that some batteries, if you do it, for example, here, if you go to extreme climate means low temperature, so batteries, it is going to be off. That's why same thing, your mobile phone sometimes here. So when sometimes too much cold, if you expose a lot of times again, the batteries. So that's why mainly due to the connectivity issues or sometimes sensor will be there, it will like a pretty low temperature, automatically it is off the battery. Again, we have to look for the long cycle life. It is like for more reliability. For example, once you will tell some kilometer, so it has to work, and we have to look for the good working voltage. I'm going to discuss in the coming slide. And also another important point to remember is that good looking for good Coulombic efficiency is almost like 99%, and resistance of the cell is during the long-term cycling, minimal resistance variation is to see. After doing all this one, we have to look for the fast charging. People may ask you, is there any way to do fast charging, either green or any type of materials you do? The problem is these materials are the solid state materials. So lithium wants to come in and go out or what are they? So for that case, so it will take some time, because of diffusion limitation. That's why the manufacturer will tell that, okay, you can charge the batteries at a particular current rate. So that you want to get a maximum energy, maximum capacity or energy density of this particular battery. Again, there is a lot of interesting things going on. For example, for smart chargers or fast chargers, etc., and also charging infrastructure, etc. Things is going on with all over the world. Again, after solving all this one, we are looking for more safer material, low cost, toxicity, and we have to look for the sustainability interest. This is very important for especially for the at the end, whatever the research you do, these materials have to be recycled. So some people may ask you that, okay, so you know that mainly lithium is very expensive. So shall we go for sodium or other alternative technology? Yes, you can do. Based on like just I summarize, sometimes people may ask that this type of questions. Always remember, if it is electric vehicles, one side is your cathode side. There we need this type of the raw materials. And electrolyte, we need some lithium containing salt. Anode side is a graphite. Usually we need something either graphite mines or some petroleum pitch is needed to heat to high temperature. And also we need something like copper, aluminum, stainless steel. These are the boards are needed for cell manufacturing. Again, you want to run your permanent magnets are needed for the electric motor. So that, for example, these are rare earth materials, whichever the countries they have. So automatically they can monopolize the marketing. So again, depends on what type of applications they like end use and the end users. So these are typically, so if you take about this nickel presently, why the cost is slightly higher, the main issue is that this type of particular cathodes, so especially this cobalt, these are elements are a little bit expensive. That's why the cost of the battery is almost like 34. Again, nowadays, still this cost is people are reducing by doping, for example, reduce the cobalt by nickel rich or manganese, etc. A lot of attempts have been made. Now I'm going to introduce a little bit more details on how the battery, how it, for example, what type of constituent of the positive materials are negative, or inside there is a separator and electrolyte, etc. Usually the cathodes is like lithium containing any metal oxides, for example, lithium cobalt oxide or lithium iron oxide or the manganese. These are the lithium. Suppose if you talk about the sodium batteries, we need sodium containing oxides, or if you talk about the potassium, we need potassium containing oxide. So why this among all this one, the presently lithium is popular because of the presently lithium is we can expect it the good high energy density. So that's why. So if you talk about sodium, again sometimes these materials are a little bit hygroscopic and also slightly lower energy density, and we don't expect the expected plot potentials. So there are a little bit difficulties. So also similarly, in addition to, like for example, calcium, magnesium, zinc, again these are all different type of, and again if you go for higher ionic radius or higher atomic number, there is a problem with your like ionic radius issues. And also we know that, for example, uh, reactivity, if you see the lithium, sodium, potassium or calcium, it means the calcium is more reactive. So try to put you simple experiment you do, just put some sample in hygroscopic solvent, again it is reactive. That's why. So the material should be, so there are a little bit challenges in the material issue. uh, Negative is you can use usually graphite now, or sometimes they use some naturally preparing from pitch, artificial graphite or natural graphite here. For example, presently we are doing mining on the extraction of graphite from the naturally occurring minerals. And sometimes we want to increase the capacity, they may use something like small silicon. So within combination with the graphite, in order to get a high capacity. So it's very important. Charge means oxidation, analytic scan, and positive current and state of charge. So these are the terms people we use. So discharge, we call it reduction, cathodic scan, and negative current. Electrolyte, we call it, for example, 1 molar LiPF6, ECDMC, ionic liquid, and polymer electrolyte. Remember, so all the understanding, for example, you would like to talk with this particular electrolyte itself, I can cover in almost like 1 hour, 2 hours, like that's why really very wide, and also, for example, all this one. So anyway, due to time limitations, I'm going to a little bit briefly summarizing the point by point, etc. So again, 2019 Nobel Prize is given to the well-known chemistry, for example, physicist and chemist is one of the oldest Nobel laureate, Professor John Goodenough. And also, in addition to the 3%, one of the other French, Michel Armand, also play an important role in the developing of this rocking chair and polymer electrolyte, especially for the lithium battery. You can see some of the early work on the 1972 with another Nobel laureate. This is the first author by Michel Armand. So now I'm going to introduce the how the principle. I think all people are familiar about the simple what high school, what we learned in the simple electrochemical, what they call rechargeable battery. It looks like there is a cathode. During charge, the lithium move from the cathode to anode, where the electron will pass to the external circuit. During discharge, again lithium will go back to the original structure. That's why The criteria for this one is which should be something, what structure should be layer, so the lithium can be mobile, so that it coincide and come back. So that is the main thing. So right side is the current versus voltage potentials. For example, your lithium cobalt oxide, you remove lithium from the structures, becomes a cobalt 3 to 4 plus, charges to balance. This is called as oxidation and reduction. So is a characteristics of any materials, you have to get a, for example, you have to get a positive and negative current. That is very useful for what they call it, the rechargeability. So another important point to remember, this is the galvanostatic voltage versus capacity. You have to see which type of the voltage. For example, is a cathode depending on the LFP or L lithium nickel or NMC, etc. We get something around 3.9 volts. Or if you go for other materials, 3.4.2 or 4.8, some depending on the materials, etc. So the major challenge is that if you want to get high energy density, we have to see the difference between charge and discharge should be higher is good. And also we have to get extended capacity, for example. So now presently we have something around 200 maximum we can go. If you go to 400 or 500, automatically we can improve the energy density. Also we can reduce the what they call as a weight of the batteries. Again, what I discussed is similarly people are so these are some diagrams. So again, how the lithium, so exactly this is the way it will move side here with both structures, for example, lithium cobalt oxide and graphite. Similarly, discharge again, whatever the lithium is coming from here, it will go back to the original state. That's why we call it the rechargeability. Still during the first cycle, there is a small amount of lithium is stuck in the layer. So that one, so that's why we call it the irreversible capacity in the first cycle. So these are a different type of mechanism. Among them, more popular is the intercalation. The intercalation means here we see there's some topotactic reactions. It means that only one or two lithium will go in and come back. We don't see much structural variation during the charge discharge cycling. So another one is silicon and tin. It undergoes alloy forming elements. As you can see right side, in addition to reduction, we can see something like alloy. So as a consequence, we can see the volume variation. The main issue is that to avoid the what they call it, to avoid this volume variation. So what people will do is that try to nanotechnology, try to put some nanoparticle, for example, silicon, it disperses in the carbon matrix. So that is the way we have to do. So another thing is the conversion. Again, these are a little bit technical academic. Sometimes the little bit challenges in this type of oxide is that how to reduce the voltage. Although we get some high capacity, practically sometimes we cannot use because of the we don't have any proper matching cathodes and some problem with the voltage hysteresis, etc. So again, for example, alloy means depending on the voltage, the same material, we can see the conversion also. So again, we can get some high capacity, some other limitation, especially voltage, etc. we take into consideration. So it's very important. Suppose sometimes any researcher or any, like for example, mechanical engineer or chemical engineer, so you would like to do research on this particular example, any type of metal ions, either lithium, sodium, potassium, or any type of things. Always you have to look for the whatever the research you try to prepare any green material manufacturing. So you should look into the low atomic weight, and the material should be what they call as a, if you want to be lithium ion battery, lithium containing materials you to look, or you should it is to reduce or oxidation is to look. And anode should be, for example, you to get lower discharge potential, cathode should be higher charge potential and high capacity. The voltage, again, a voltage, repeating the voltage in the cell is nothing but average potential of the charge minus discharge. So again, so depending on the this, for example, you can see this particular iron phosphate cobalt, comparing all three together, top one is slightly higher energy density because of the voltage is also higher and capacity accordingly. So now major challenge is that suppose whatever the research we do, so suppose if you're able to extend this one, maybe presently I think around 180 is around 200. Suppose if you are able to get some smart materials to go up to 400 500 capacity, I think that will be really good. We can reduce the cost and also we can improve the energy density of the particular unit type of the battery pack. And also we have to look for the material should be stable with suppose it won't react with electrolyte, etc. So and also is another criteria is that suppose people are talking about fast charging. For that case, we need some material should be mixed ion conductors, and it is very important always. Anyway, this one further people can do improve the this type of pickup, something like the people do some carbon coating or a graphene, some few other type of the coatings also you can do. In summary, so because of the lithium materials, because of the lightweight and high, because of the high volumetric and gravimetric energy, lithium batteries have been used for the different type of applications, including portable as well as space or drones, etc. So now again I'm mentioning that another important metric point to remember is the electrolyte. Either you can use something inorganic electrolyte, for example, lithium-based system, you need lithium containing salts, or if you talk about sodium-based, sodium containing salt. So for example, again, remember conductivity is conductivity is really good. Also, there is a problem with leakage and flammability issues. That's why people have looked into other alternative, for example, polymer-based electrolyte, again, polyethylene oxide, and then the combination with the gel polymers, or something like ionic liquid in combination. Again, at least we need slightly higher temperature, around 50 to 60 degree needed to get a reasonably good conductivity. Separators are the important components to avoid short circuit, and we have to look for the appropriate thickness, porosity, and good permeability, and low electrical resistance, and good tensile strength. So it's very important once you make a big cell, again, if by mistakenly your separator is going to be some hole or puncture, so that maybe leads to short circuit. That's why, so sometimes it may catch fire also. That's why some type of the batteries, that's why it's very challenging. Everything should to quality control, including the cathode, anode, and electrolyte and separator, everything you have to be taken into consideration. So sometimes recently, sometimes because safety due to flammable electrolyte, again, people recently, like either due to the electrolyte problem or due to the oxygen release from the structures, also some problem with the malfunction of electronic circuits. So that's why one approach is the use replaced with a solid liquid electrolyte by all solid state batteries. Again, you have to make some ceramic oxides or sulfides mixed with some cathode and oxide to the cathode material. You can press by using some additive manufacturing or sometimes hard press. So that's why something like a lot of opportunities, especially what you use, for example, spark plasma sintering or any hard press, you make a big dense ceramic membranes. So that when you can use it for, again, little bit challenges are that if you go for high temperature sintering, there is a reactivity interfaces. Sometimes you may reduce the conductivity. Also, sometimes you want to fast charge, discharge rate. Also, a little bit difficulties are there. So, and also we have to look into chemical stabilities and other important cost and toxicities. We are not really bothering about this one because although in the initial stage, still I think people are putting further cost. Sometimes they use something like some polymer membranes. Again, the polymer membranes we do sometimes conductivity may be reduced. So these are the different type of the sulfide-based electrolyte. Again, advantage is that their conductivity is reasonably good when compared to especially oxide-based systems are a little bit easier to prepare. Again, so we need high temperature to make a processable ceramic membranes. So that's why here we need to develop the, for example, additive manufacturing or spark plasma sintering or hot press sintering membranes. For almost we need something roll-to-roll membranes are needed for the large-scale applications. Anyway, another area is people can use it by their lithium air just to protect the lithium metal for aqueous air, because your batteries are your redox flow, or you can use it for your all solid state thin film battery, etc. So now we can talk about, we're going to discuss about the what are the different material processing and fabrication techniques. So either usual ways that depending on applications. So again, it depends on what type of research area we're focusing. Accordingly, we have to identify the materials. Again, try to understand structure, composition, and size and shapes. Again, it is very important the material processing and understand the structure and especially characterization of the material is very important for doing any material for before doing any applications. So this is one example. For example, either sometimes you may get some depending on size and shapes we can do, although we can do it in the small scale in laboratory. So now with the industry, I think for large scale appropriate, because whatever the size you want, people can, I think especially chemical engineers can design the materials, especially reactors. They can prepare it with almost like quantity in the tons of the quantity. They can, for example, lithium iron phosphate or layered cathodes. Already people can be have been demonstrated to prepare the samples in the tons of the quantity. So usual way is the chemical methods are good because so we are in case we need if you want to prepare samples in large scale, I think these are the really what they call viable. Or you want to make some thin film coating, yes, we can do again. So because if it is thin film batteries, we may not get high energy density. That's why. So at least we need the bulk materials again. Advantage is that we can get some desired composition easily when compared to a thin. For example, you do sputtering. Again, you do layer by sometimes you may need the composition optimization or sintering. You need different more complicated techniques. And again, these techniques are very useful. Suppose you want to be prepare, for example, CVD or MOCVD, etc. We can use it, for example, silicon. So this type of this, for example, solar cells, all this one, they can use this type of particular technique. Again, for example, people, although irrespective nano size or not, whatever the size, especially for mechanical engineering of our, so our composite engineering materials, I think they are looking for the material should be good mechanical property. For that case, we need something like we have to use something like powder metallurgy approach or something, for example, hot pressing or additive manufacturing or 3D printing or spark plasma sintering is very important. Anyway, this type of the applications people can use it for the different type of the, for example, solid oxide fuel cells or solid state battery or the making preparation of supervised or composite, etc. we can use. So a quick slide, for example, what are the thin films? Either you can get to, we can get the thin films either by chemical vapor deposition techniques or physical vapor deposition techniques. So, or suppose you want to prepare IC films again, we need something like ALD, PLD, or CVD, chemical vapor deposition, or molecular beam epitaxy, etc. So what I am mentioning that depending on the applications, again, thickness is very important. Some particular thing is something like nanometer, or sometimes we may need thick coating again. So they will see the mechanical composition, surface and interface effect and good mechanical properties or addition, etc. is needed depending on the applications. So these are the various techniques. For example, usual way that whatever the materials you try to prepare, characterization is very important. X-ray is very useful tool. Just especially for battery, you want to see the cation mixing or some impurity and lattice parameter, etc. is to match. So especially for cathodes, we need some material should be pure. Then only we can get a desired performance. And for example, thin films are there. You would use something nuclear reaction, RBS, and nuclear reactions, or if it is Auger electron spectroscopy, etc. And another technique is the ICP titration techniques are also needed. And also, for example, these are the different type of softwares are needed. And also we need something like morphology by SEM, TEM. Or for example, in the battery, we need something like chargers and impedance analyzer. Also, we can see something like physical bulk density or surface area, or sometimes we want to study the other physical properties. We need this type of the, for example, magnetic and Raman spectroscopy is needed. So these are the different type of the techniques as we can use. There are some are routinely XRD people can use to characterization of the any material researchers. So for example, the importance of the X-ray, just you would like to see the, so your materials are amorphous or something like some nanocrystallines or something depending on the crystalline or depending on the temperature, we can see difference in the crystallinity or average crystal oxide, etc. Usually, for example, if it is nanomaterial, you can see something like line broadening, we can get, or if it is crystalline material, we can get very sharp peaks, etc. So also if it is thin films, we can see what type of the layer, for example, different type of layers you can do by using glancing angle, X-ray diffraction, etc. So advantage, some people are looking for, you want to see the, what they call as this particular selected area electron diffraction. For example, some nanomaterials, we can compare what this particular HK lines we can get by using because the diameter divided by 2, 1 over D. So this interplanar D value is, what are the D values corresponds to what closely near to what the value you're getting from the XRD data. So that's why these are a little bit complementary. So overall, in summary, TEM or XRD delivery, you try to understand is useful to understand materials. For example, if it is amorphous, nano, or polycrystalline, XR crystalline, etc., or any type of phase transformation, etc. So in general, I think today my presentation maybe I'm going to so mainly focusing on the including all material researcher, including all type of any engineering will do it will comes under the 7 crystal space group. Maybe due to time limitation, I'm touch up some few examples in the coming slides. Regarding the battery characterization, I think we need something like a battery tester and impedance analyzer, and also we need something like other technique like cyclic, and for example, you want to see the conductivity measurements, you need something like furnace or two probe conductivity setup. So what is the fast charger is nothing but this particular setup. It will monitor the voltage from lower to lower limit, higher limit, and it will maintain the constant current, and the capacity we can calculate based on how much time multiplied by current divided by the weight of the active material. So advantage is that if you want to calculate the energy density, power density, so this type of the techniques are very useful. So it is typically depending on the already mentioned that you want to see which material is high energy density, or we can calculate, for example. So I already discussed the energy density of the cell is in voltage into capacity. If it is power density, the voltage into the current, etc. So again, I think these are the formulas. It will be useful. You want to calculate theoretically in experimental capacity. And then, so irreversible capacity is very important. That's why during the first charge discharge, you have to get a minimal. These are some example. I have higher ICL. So these are really good. For example, graphite is lower ICL when compared to your fuel air graphene, or more high surface area. Although we climb this type of materials, it may not be really good for the practical applications. Again, you have to get some lower capacity fading, means difference between the discharge with the N cycle, for example, second minus 50th or 5000 or whatever the number divided by second cycle. You have to get a minimum values. That's why we can tell the capacity fading. Coulombic efficiency difference between the discharge minus charge. From there, we can calculate the Coulombic efficiency. I think rate capability is also means, for example, so these are all like 0.1 C means like C by 10. You may get some capacity value, the same value, for example, 5 C means 12 minutes. You can see depending on the material, the capacity is going to. That's why sometimes any battery charger or any people or any supplier, they'll say, okay, please do with the particular program. They have something, all the program is installed in the particular EV charger. They'll tell, okay, so that's why you would wait for some time to charge. Always they do it low current rate, because the idea is that they want to extract the maximum capacity as possible. As I told you that these are solid state material, there is a problem with the diffusion limitation. That's why they may tell that, okay, you have to charge it a particular with some time. That's why in order to get a good capacity or good kilometer, etc. So other important point to remember for electric vehicles, again, you want to be something like material and porous design. I think they need something appropriate, not like too high, too low, also not good. So we need appropriate, and we have to look for the good electronic conductivity, and also electrode design, and current collector modification is very important. Again, for the high voltage, again, cyclic voltammetry very useful tool just to understand the, for example, reversible peaks like oxidation and discharge. So it will very useful. What type of the material, depending on the materials, for example, 4 volts, 3.5 volts, or so automatically it will tell the information about the voltages and redox potential, etc. So again, it depends. Suppose sometimes people are working with a supercapacitor. So there we can do with a carbon-based system, or your Faraday due to the something depending on the some metal oxide, etc. So again, so this is all I can do. Until if you go more depth, you can do. We can understand the what you learn from the textbook electrochemistry, or what you learn from electrochemical engineering courses. There we can calculate the diffusion coefficients, etc. Or you can see the variation of the scan rate, etc. I can do. So another technique is the impedance, is like to see the resistance is like high frequency analyzer. So there, so what we're going to vary the high frequency to low frequency at a small AC amplitude. So from there, idea is that just you want to get the information about what type of resistances. So again, this technique is very useful for the different areas, not only solid state ionics, or for example sensors, different, for example solar cells, fuel cells, supercapacitor, etc. Again, we can understand the electrode electrolyte interfaces, diffusion rates, etc., and reaction kinetics, etc. So anyway, typically, at least you want to see something like when you have any conductive membranes, or just you can do a pellet, and you can coat it either by blocking electrodes. Sometimes you there, from there based on the resistance, by knowing the resistance with the thickness and the area of the electrode, you can calculate the conductivity of the any type of the material. So either usually a battery, you can do something like 2 electrode system, or they want to be more advanced, you can do either 3 electrode systems also you can do. Again, so most commonly 2 electrode systems are practical applications. So for example, your ceramic membranes or any electrolyte, at least you can see what type of the bulk or grain boundary resistance. We can calculate from there, we can calculate the energy activation or so our particular contribution conductivity to this particular semicircle also we can define and we can explain. So again, I think I'm going to quickly, I'll go through, these are the people are interested, maybe some people are particularly doing the impedance. I'm happy to, maybe you can send me email. I'm happy to answer some more details about how to, what are the experimental conditions, for example, here. So we can, how to interpret this type of spectra. I think we need something like resistor, capacitor combinations. Again, so something like surface phenomenon, charge transfer, etc. So overall idea is that it is really complex and we can understand. I think this technique is very useful, is non-destructive without opening any cell, just you put the lead and just see the response. From there you can tell the how the battery is good or not during the cycle number or etc. I can do. It is like another like life cycle estimation of the battery. Anyway, you can do a lot of complex modeling, again depending on really what type of things you want to do. Again, you can do very different type of systems you can use. We need appropriate some knowledge on the how to interpret the spectra, isn't it? Anyway, these are example of the different systems, like this is a solar cell, and then this is typically something Panasonic batteries, etc. So in summary, once you made a detail, this is a big battery pack. Not only suppose you want to be system real design, like a real EV vehicle. Not only I think it is very important once you make a real battery pack is ready, you have to talk with your mechanical engineers or electrical engineers just to integrate or try to understand this all this particular pack is very important. So is overall summary that we need some understand the power electronics and especially electric machines. Again, this is the contribution of triple E people, and here from the mechanical engineer, also materials, for example, battery management, etc. So whatever the things there are thermal management, and again, other things also energy storage part also take into consideration. So for example, if you talk about battery management, there are challenges. That's why too many cells we are putting, and there is sensor. For example, all the cells is charge discharge has to do with a constant, whatever the program it tell automatically to do, or sometimes to cell, for example, they to monitor the sometimes like temperature, etc. I think that's why we need something like smart sensor, and also so for example, so each some particular cells is charging fast or discharge. So there are all things you have to take into consideration by using the battery management. So these are typical example. You can see during charging some particular, but this is battery is really good. Other one sometimes we can see the voltage differences, etc. Similarly, with respect to discharge also. So I'm going to now. So I'm going to discuss some few example on the what you try to what are the materials you prepare again. So we have to see that how the performance of these batteries. So there's a typical example. So these are the cathodes usually. So that's why you see the capacity, the y-axis. Some although anodes we may get some very number. This side, top side is we are not able to improve much. So that's why you want to make high energy density. Again, the positive side and negative side also capacity is to improve. So that's why, so there's a little bit limitation of this one. That's why the material challenges also there. That's why we need something like good material manufacturing in a large scale, and especially it should be high energy density is very important. So usually as the industry, they're not bothering to take existing material. Either they want to make more capacity just to some protect the surfaces. And again, so we can use the this type of the what are promising materials, especially that they are already running with some materials for the EV applications. So these are the well-known materials. For example, nickel, lithium, nickel, cobalt. They are already used in the commercial batteries. And again, the presently limitation capacity is the maximum, I think around 180 to 200 it can go. Again, there is a lot of challenges look for the high capacity materials. I think these are a few examples, some of the high other materials. So this is one example. If you want to prepare the materials either by oxides, nitrides, sulfides, or composite, I think graphene or carbothermal reduction method is very useful. Usual way is that if you want to take metal oxide to reduce to higher to lower oxidation, we need a calculated amount of carbon. We try to put it in a high temperature furnace, means around 650 to 750 degree needed to react with the carbon. Once it's ready, we can put the sample either with an argon or ammonia. If you want to be nitrides, you can try to prepare. and finally the cell is ready, and you can prepare some respective oxides, or if you work with catalysis people, they need some metals dispersed in carbon. So accordingly, we have to use more carbon. Again, you can play with it depending on the which type of the process parameter. Remember, these are all the small scale. Really, you can see the same furnace, especially for industry. I think now they have capabilities to prepare nearly tons of the quantity, like big reactors or big furnace already been developed. In the, for example, we know that the graphite extraction, there is a there is a lot of activities by especially mechanical engineers in, and developing the big furnaces or big machines, especially there we need almost like tons of the quantity preparing at a batch to batch scale. So these are the one example lithium vanadium fluoride. Here again important is that you have to remember oxidation vanadium 3 plus to 4 plus. These are the redox couple, and these are the expected charge voltage. And reasonably you have to see the phosphate oxygen is reasonably good thermal stability. So anyway, we try to prepare the samples and we can characterize them by XRD and other techniques. And usual way is that once it's ready, the powder you can mix with some conducting carbon and binder, put together, try to coat it in the copper or aluminum foil. This is the current collector. Then roll it, and then punch. Suppose you want to use for coin cell, good small circuit, whatever the dimension you want, you can cut it. For example, you want to be bigger cell, you need a bigger pack, you can cut it and try the things. Then it's ready. If it is a laboratory, use some glove box, you can try to prepare the cells. Usually in industry they put something like mixing, coating, everything is automated, so the only is a matter of money. So we can buy a lot of big equipments are able to. Also remember, as academic or any university, the people, nobody is willing to prepare kilograms of quantity. All this one is, that's why at least you can do something like coin cell or a small scale fabrication. That is enough for you to understand the principle and high energy density, etc. Once is a promising material, I think many people are willing to take our technology or materials for the future applications. So this type of coin cell, for example, this bottom gap and your material there, and electrolyte and separator and lithium metal, finally the cell is ready and we can try to prepare the sample. So these are typically, as an industry or anybody, they do small scale cell. Once is promising for each batch, then they can go for the large scale. That is the way of quality control of any materials. This is the charge and discharge potential of this particular material, and we want to see the capacity, how long last this, what are the value you are getting somewhere around this one. For long term is almost like 6 months, reasonably good. Another important point is you have to see the, for example, among 3 cathodes, you have to see the voltage, it means 3.5, 3.9 or 4.2. So among them, this slightly we can expect the high energy density or due to the high voltage and reasonable capacity. Again, we can do, so we can do further studies with a lot of techniques, what are the possible mechanisms, etc. So it is very important. Idea is that whatever the way you do high energy density, means to see the what type of plateaus with the top and down, and which accordingly you can design which material is good or not. So that is by experience you will learn. So that is my personal experience. So again, I think in this direction we look in some new materials. So with the 4-volt materials, again, so something are green. So we can try to prepare sample in the green solvent, for example, with a simple hot plate stirring. Example, this type of particular compound. Example, this compound we've been prepared in nearly hot plate with a low temperature. Also, you can try to prepare these are metal, organic, inorganic framework materials. And advantage is that if you compare 3.5 volt iron phosphate commercial, nearly 4 point means slightly higher energy density we can expect by using this one. So these are the typical, for example, 4 volts cathode materials and capacity versus cycle number, etc. So and also we ask you what is the effect of these particular materials with the potassium ion batteries. Again, you see that hardly we are able to get nearly around 30, means almost it is less capacity when compared to your lithium. We know that potassium ions are slightly ionic, there is a mobility. Also in addition, the other one is the electrolyte. Anyway, still recently some other for other colleagues from Japan, based on our first report, I think with different electrolyte they have been improved further, improvement in the capacity. So some other new materials in the phosphate containing compounds with early report 2012. Later, including Nobel Prize, Professor John Goodenough and Whittingham, they've been looking into this compound, and then I think from other groups also they've been now they look these materials for, especially for large scale applications. People are looking into this type of material. Again, so some other the important point you to remember is that, especially for the cost, sometimes people they ask you, okay, they will see that shall we use sodium, because since sodium is plenty of sodium are is available in the universe, or like a lot of different sources we can get. So the main issue is that you see that in terms of the weight slightly higher. Again, maybe in terms of reactivity, the sodium compared to water is more reactive, especially compared to lithium. Again, potassium is more reactive to sodium. Again, if you talk about calcium, it is more reactive to the other elements. So that's why. So it's just a matter of the flammability and safety issues, material. Again, another important people they will consider is that voltage. Although sodium slightly lesser voltage we can get here, still for example, for the practical applications, although so slightly for lithium base is 4.2 volts, we are getting same material prepared sodium compound is 3.5. Although we get lower energy density, so this is a way to compromise with respect to cost and energy density. For example, for stationary grid, so there, so small difference in the energy density we can manage by the compromising the cost, so that okay. So another one is the last, I think the second part is a little bit anode materials. Again, since I have already finished almost 55 minutes, so I think I have another maybe another 15 to 20 minutes, so that I can take another 10 minutes for question and answer. So quickly I'll go through the some important of the what are the anode materials. Again, people most commonly graphite, or sometimes silicon, little amount of silicon they use for commercial, because in order to get high capacity, and sometimes lithium metal if it's a all solid state battery, etc. So typically graphite is very famous because of the lower potential. People may ask you, why don't you use fillet graphene or graphene? Yes, we studied some example. You can see that although we may get some high capacity somewhere here, see that we will see higher ICL. This type of profile, it may not be good for the practical application. Whatever the research you do, make sure that we have to get something like capacity in the lower potential is good for the full cell fabrication. Again, say this carbon-based system or graphite, they can use it for the different type of the application. That's why industry they think about. So although say if it is a mining industry, they will think about so materials they will not throw. Although depending on size, they can segregate it, or with that one they can use it for the different type of applications. So again, there are different strategies. The nanotechnology, matrix element, and conductive matrix elements also will play an important role. So again, so these are the different type of techniques people they use to understand the mechanism. If you consider alloy-based materials, again you talk about tin and silicon. So these are the that's why nearly 0.2 volt. That's why this is reasonably good. And silicon is certain waste systems are slightly higher discharge potential. Among them applications, they look for the top two is really good, so that both are matching. So among them, so some of the few tin-based systems with red belongs to our group at National University of Singapore. Again, these are the few compounds have been, new materials have been explored. Among them, you can see these are the bunch of the, also if really people are interested, I'm happy to provide some of our review. So what I'm mentioning that a lot of challenges again here is how to reduce the voltage hysteresis, especially for the practical applications, and also irreversible capacity in the first cycle is very important. So this one approach is that if you try to prepare some new materials for nano size, and we need something conductive to matrix like cobalt and vanadium, they're really good, and is almost like reasonably good rate capabilities when compared to the submicron size material. Again, the reason is that we saw that like resistance of the cell is almost like unchanged, etc. So another important point to remember, especially some conversion based oxide, there is huge materials also there. Among them, you see this, for example, the main issue is that how to reduce the, for example, this discharge and charge potential should be further down is good. So that's why, although we climb some capacity, we cannot do matching cathodes we don't have. So there are a little bit difficulties in this particular areas. Anyway, I think like similarly, you can do what are the material manufacturing you can do. You need appropriate way, and you can do. I think another important thing is the nitrates. So advantage is that you can compare to your oxides. 3 lithium can be reacted. So in the sense that we can get extra lithium, we may get some extra capacity. So idea is that we look into the nanoflex things followed by bulk materials also we've been prepared. Again, these are the trend, nanoflakes, bulk, and then also we look in some hard materials, again, chromium, titanium, and then tungsten nitride. These are very hard. I think electrochemically, they're not really good. So again, the challenge here is again the same issue, that how to reduce the voltage hysteresis is a big issue for this type of oxides. And again, some other category I told that intercalation, among them Li40, F12 is a little bit good because of the we can get lower discharge plug potentials. Again, these people have been studied these particular things with respect to the high voltage, another 5 volts LIMN, nickel 0.5 Mn, 1.5 volt cathode materials. So I think one example, if another something people are talking about nano TiO2 is already well known. People can use it for either electrochromic or solar cell or photocatalyst batteries, paint, and other biomedical industry, etc. So again, you can try to different ways are there. You can try to prepare a different what I'm doing with molten salt approach. With you take a appropriate nitrate melt with the titanium oxysulfate, put alumina crucible. So here, without any surfactant or anything, we can get something like high surface area materials. So these are one example. You can use something like 280 degree. We can get almost like 200 meters square per gram surface area. Our idea is that if you go for nano size to submicron size, how the energy storage performance, etc. It seems to be this is very special. Usually, so we to be good reactive, because since these are semiconducting materials, we need material should be nano size is really good for the application. So again, some small improvement also we can see by using the DSC applications. Also recently, some people have already demonstrated with the photo battery approach by using the DST or to DSSC applications. Again, the importance of the semiconducting material as a TiO2, we can use it for a lot of sensing application. Again, you want to be conductivity sensors or your ATS stabilizer zirconia. These are the ceramic electrolyte or ceramic materials for the, for example, gas sensors or especially automobile exhaust or some different type of other sensors, etc. So again, I think there is another story. Again, some materials without any fast organic electrolyte setup is there. At least you can do something like I can do academic research and carbon based or metal oxides, or in combination you can do. So again, main issue is here is that you have to restrict the voltage to 1.5 because you're using the aqueous based electrolyte. So that's why. So again, you can do some organic. The problem is that sometimes you may not get expected capacitance what you're getting from the aqueous electrolyte. So I think some people are maybe what type of other things you can use some organic base. Again, the challenge is that we may get something like lower energy density. So if we want to practically use this one, we have to get something like nearly 4.2 or 4.0 volts is good for the practical applications. I think this is one example with iron phosphate. Also, we can use the high-rate cable material. So idea here is that we need some conductive carbon coating for the practical applications. So anyway, so as a mechanical, some of the collaboration, I think we did some work with mechanical engineers. I think so. Although depending on expertise, I think people do some electrospinning technology, want to make ceramic materials or fibers, etc. Again, the what type of temperature depending on the polymer precursor decomposition temperature, we can play with the either fiber or something like a different type of the depending on polymer, we can see the different type of morphology, etc. I think this one quickly I'll go through because the part two is that I think there are a little bit more on once you make a big device, what are the real challenges? For example, design and thermal management and failure and mitigation strategy if possible. So these are the typical battery pack. Again, so the main idea is that battery design and battery production. Again, EV application because the charging facilities are all things. And second life in the sense that, for example, use battery, they can use it for the other stationary applications or any other things also. We look into this one or so that's why idea is that just to extend this life cycle of the, for example, battery for the secondary applications. So again, there's a lot of challenges, although you can do material design, electrode level, cell level. Again, the how we are fabricating, the importance is the mechanical and thermal battery management. Once you make a real cell, all the things are taken. Very important factor is for large scale, again, the pressure stuff, the stack is also very important. We need something appropriate pressure. again, the importance of the mechanical engineering is sometimes these are all the things people, again, appropriate casings, appropriate things just to vibration, etc. People can use. There are a lot of interesting things are needed, especially you go for the large scale device. Another important is the temperature sometimes. So we don't want too low temperature, too high also. That's why. So these are the little bit optimum temperature also needed to run this one. Or if it is go and up and down, we need something like additional system is needed, for example, heating or cooling the battery pack. So again, we have to understand the influence of geographical location, climate, weather, and season, and also cell design, vehicular design, and all together for again heat capacity, thermal conductivity, and for example, resistance and current, and then the thermal management system, etc. That's why they're all the importance of temperature. These are the key challenges. I think cost is also very important to solve safety, and again, high voltage cathodes need and safer electrolyte also very important, and mainly battery management. And now I think life cycle, for example, once you do charge, is there any way, for example, got higher, maybe more than 300, 400 kilometers is possible, or is the question mark? Again, you have to understand the climate condition, example, low temperature batteries also. I think thermal stability is very important. Sometimes already I discussed about the either due to the electrolyte problem or due to oxidation release by material. Again, you have to understand either sometimes due to the, so there are different factors are there. Again, so either usually, so how to mitigate that one? Either sometimes you want the heating and cooling the heat, or sometimes any fire is there, either you can do. So we want to cool it externally or internally. So there is a lot of things, for example, a lot of mechanical engineering things, it will play an important role. That's, for example, you want to be mechanical, electrical, these are all the different way of the what they call a thermal failure mechanisms of batteries. That's why it is really complex. That's why sometimes some batteries, some particular batteries are also, so the same make some since we do too many cells, sometimes one battery is going to be failure or some problem with fabrication or some contacts. You may see some difference in performance, etc. So again, the material failure mechanisms, especially for the anode side, there is a reaction with solvent. Also sometimes a rapid charging, again something like dendrite growth will be there and leads to short circuit. If it is a, for example, manufacturing defects, also sometimes you can see the reduced battery capacity, or if it's problem with the reaction with solvent, you may see the solid electrolyte interfaces due to power fade. Also sometimes due to the decomposition, sometimes you may see the thermal runways, etc. So anyway, these are the little bit same thing, whatever I discussed, these are the different way. Or if it is a graphite, they call as something like dendrite growth. Sometimes it may puncture your separator, sometimes you may see the battery failure, okay. So again, in terms of the cathodes, again, overcharging, we can give cathode decomposition, again, which leads to thermal runway. Sometimes the exothermic reaction with electrolyte also reveals oxygen, again, that will lead to the thermal runway. Another failure mechanism, sometimes you work with electrolyte, again the temperature, sometimes if you go to high temperature also there is a thermal runway. Sometimes separators, I already mentioned that some separators there is short circuit with the contact, that is also lead to the thermal runway. So anyway, if you not avoid this one, sometimes people they use some electrolyte additives, so just to reduce the heat. So these are typical some of the commercial electrolyte additives we can use. And sometimes current collector mechanisms, either sometimes copper. We know that copper is to negative side. That's why if you use the above 3.5 volts, copper dissolution or reaction will occur. Again, the aluminum maybe more than 5 we cannot use, or lower voltage it react with lithium. So these are the different mitigation strategies, either intrinsic safety, either due to cathode alteration, anode alteration, electrolyte, and again battery management, safety devices, safety vent, and safety circuit breakers, and thermal management, either you can do air cooling, liquid cooling, or phase change materials. Again, mechanical strategies. That's why I'm telling that these are very important point. Is a lot of any interesting, we can, a lot of mechanical engineers we can work together. So again, after I discuss about this thermal management or phase change materials, again the importance of the, for example, liquid cooling, people they can use something like nanofluidics or some liquid metal they can use, especially phase change materials. For especially EV vehicles, they use something like aluminum foam, graphite matrix, and copper foam, etc. to optimize the heat conduction. So these are things, okay. I think one last slide, I'm quickly I'll go through sometimes until that you you buy some battery pack, there is a safety limits. So what I'm telling that make sure that what are the limit they suggest accordingly cycle don't exceed the limit. For example, if you exceed limit, I'll tell that with in situ XRD technique, you can tell that okay. So what are the battery packs? Sometimes if you exceed the limit, they may see something what they call as a huge volume variation lattice parameter. For example, you can see here when you remove the lithium from the 60 lower 2 theta angle, go to further lower it means as you can see the volume variation. That's why sometimes with the safety limit. So for example, this particular battery they will 4.3 or 4.2 volts. You can restrict to that voltage. So in summary, you can do some other fancy technique. For example, neutron. There are all things you can do. So what are the accessible facilities or some NMR or more fancy techniques also you can do. Or sometimes you can do some synchrotron facilities you have. You can do the real time how they be doing battery charging, discharging, what is going to happen with respect to I think last one slide, I think sustainability is very important. Whatever the research we do, so we have to recycle the materials. So that's why it is almost like 900 million electric cars by 2050. Again, almost 11 million metric tons of the spent batteries been discarded by 2030. Our job is to maintain again, to reduce the ecotoxicity and then global warming. Again, you have to remember too much waste we generated this, but again, we have another problem. That's why our job is always people are looking at alternatives, direct and hydro and pyrometallurgy approach. Among them, I think industry already demonstrated pyrometallurgy seems to be good. Although we can do hydrometallurgy, again the problem is again water. Again you have to do water purification. Again the effluent treatment. Again it will give some additional cost. And that's why. So especially for recycling industry, the cost is also a major factor. That's why these battery packs, some of the cost also included during the purchase of the vehicles, etc. So that's why the usual way the discharging, dismantling, and pre-treatment, and finally we can recover by using the different approach. Among them, pyrometallurgy has been. See, for example, your lithium cobalt oxide is there. Just what you people do, they make some carbon or whatever the carbon you get. So it will precipitate as a lithium carbonate plus cobalt. So then we want to be react and then further processing this carbonate. They can use to prepare the material for again that is the way the recycling will work. So I think since my time is almost like they given me, I think 1 hour 30 minutes I have to talk. Maybe probably I finish almost 1 hour 15 minutes with introduction all this one. So maybe another 5 to 10 minutes I have. So if you have any question and answer, I'm happy to take into consideration. Again, I'm reading some small conclusions. Whatever the way you do. So again, the large scale manufacturing is very important. Whatever what they call as the zero liquid discharge. Again, it depends on what way. Sometimes with electrical engineers, we need thermosensors development is needed. Our overall summary is that we need novel materials for especially to improve the further energy density. That's very important. Again, for large scale, all the including that all engineers are engineers and chemical engineers or material engineers or electrical, all engineers and scientists should work together for the large scale applications. I think thank you very much. And then if you have any question and answer, I'm going to take some questions. Okay.
Thank you, sir. Thank you so much for such an intriguing session. And indeed, we all do realize that batteries are the new age revolution. And if anything could be done in energy storage system, then we can really revolutionize the world again, once again.
Okay,
So
sir. Thank you.
now the house is open for all the participants. If you have any query, any question, please feel free to ask Dr. Reddy. You can unmute yourself and ask. Please, all
Or
the participants.
if any charts, they let me know. Or if people
There
are,
is a question in chat, sir, actually.
yeah, if people are anyway some shy and later you can send me something, especially for students need some more information. I know that it is difficult to digest all the slides within 1 hour or 1 hour 50 minutes. Maybe later people are like particular topics are interested. Maybe I'm happy to answer. You send me my email. Already I'm putting so that so that so do you have any questions and answers? Maybe I'm happy to answer. Okay.
Any participant, do you have any query?
Okay. So
Yes,
this
sir.
is
Sir, I have a question, sir.
yeah, yeah. Please tell me, sir. Please, yeah.
Sir, is it wise to focus toward the manufacturing of batteries with additive manufacturing?
Oh, yeah, this is a question mark. I know that is like I know that you're mechanical engineers. Usually, additive manufacturing maybe is okay if you work with all solid state battery. So, for example, there is a one thing called as a all solid state battery. Again, if you the main issue is that again there also if you go more depth, so sometimes if you do additive manufacturing during sintering with the electrode electrolyte, so there is a problem with the reactivity. So additive manufacturing is a one way, good way we can do. It is not like straightforward. Like for example, you take some superalloys, melting. They're all things a little bit good. So here is a little bit since your lithium containing compound, there is a reactivity issue. So it's not because of your additive manufacturing. There's a problem with the material. So they're a little bit challenging. That's why. So especially you want to make it recently. People are talking about the all solid state battery. There, additive manufacturing will we have to. I think that will be good. Especially only main issue is that today you are able to make a ceramic membrane with almost like big roll to roll sheets is a little bit challenge, so that is a little bit challenge in this particular things. Okay, that's why. So if you people have good tricks to make this any ceramics with this type of with tricks is very valuable, very useful for the society.
Thank you, sir.
Yeah.
Anyone else, if you have any question, please feel free to ask all the participants. Dr. Reddy, I think that will be all.
Okay, sir. Okay, okay.
Thank you
Yeah,
so much for giving your
yeah.
time, sir. And I hope
Okay.
we'll coordinate again soon enough.
Okay, sir. Thank you very much. And for me, almost 2 o'clock. Okay, it is
Oh,
sleeping time. Okay, okay. Thank you very much, sir. Thank you
thank you
very
so
much.
much,
Okay,
sir.
thank
Thank you very
you.
much. Thank you. Good night.
Okay, okay, sir. Good night. Thank you very much. Okay. Yeah, feel
Yep.
free. If anybody have any questions, send me email, and I'm happy to answer. No problem. Thank you.
Sure. So we'll forward it to you, sir. Thank you so much.
Okay, sir. Thank you very much, sir. Thank you. Right. Bye.
Thank you, sir. Right. All the participants, an important announcement. You all are aware that we have exit test scheduled post lunch session. So I request you all to please join the session at least 5 minutes prior to the beginning of the test, which is scheduled at 2:30 p.m. today. Uh, if any one of you is not able to join on time, then he or she may miss the link that we'll share for your examination, and then that will be a loss because the examination link will be shared just once. So I request you all to be there on time. Don't be late, and wish you all the best. We'll meet again for the last session of our faculty development program, which will begin at 11:45, just 15 minutes from now. So we can take a short break and then we'll see you soon. Thank you so much. Thank you again. Deepak, am I audible?